Welcome everyone. This is Desi Vijay. I'm a NorthSouth National Team member and a coordinator for webinars. I'm glad to see you all here today. We are here for the session 2 of AIME 1 live solutions. Today we have two math wizards here. Right now, Eric Wong is here and Treya will be joining us a little later. And so they will be handling the rest of the problems. And we know in session 1, Siyash did the first five problems, and the other problems these two will be tackling. So be attentive. Let me introduce Dr. Sri Priya Raman is a moderator today here. And we also have Vinay, who will be helping us with the questions. Sri Priya is a parent volunteer for math subject matter experts, a subject matter expert team, and the team has put together several live problem solving sessions in the last 2 years for high school level and competition for AMC 8, AMC 10, AIME, even math counts, everything. The team has also organized several sessions with the North-South families, such as AIME Prep Club workshops, Meet the Pros, webinar, Wise and Well workshops, and math newsletters, and etc. So they are all very active in the math arena, and they have devoted countless hours towards this. Here is Dr. Priya. Would you introduce Eric or?
If you could introduce him, I don't have his bio open here.
Okay, yeah. I will do that.
I know Eric personally, but
I know. We have Eric Wong here with us. We have seen him before in our math MTP webinar. Eric Wong is a senior in North Allegheny High School, Pennsylvania. He is fond of math contests, has qualified for AIME 3 times and US AMO in 2021. He is also an enthusiastic teacher, and he's a teaching assistant for North Allegheny School's linear algebra class, in which he lectures weekly on combinatorial applications and linear algebra, and a regular contributor to his school's math and physics club. In his spare time, he enjoys writing geometry problems. So welcome, Eric. And Shreya will be joining us later, and then we will talk about her when she joins us. So Eric, you can take it. Priya, if you want to say something about AIME.
I wanted to say a couple of things. First of all, thank you for everyone to join for joining with us today. And I'm glad to see that 50% of our audience is 8th grade or less. I hope you know what AMCs are about. These are high school level competitions, AMC 10. Anyone under 10th grade and below can take it. So, if you're going to be in the 8th grade or 7th grade this coming year, you can still take AMC 10 for 2022. Or 2023. It's usually given in January, February. I think they changed it to November, February, December this year. But regardless, think about it, Google it. We have the link in the registration email that we had sent out. Mathematics Association of America hosts the AMCs, and high performing students from AMC 10 and AMC 12 are invited to participate in AIME, which is the American Invitational Mathematics Exam. So it's something that you should be proud of to put on your resume for colleges if you were qualified for AIME like 2 times, 3 times, 4 times, whatever. Even 5th graders or 6th graders, as young as 5th and 6th graders, have qualified for AIME in the past that I know of. So your grade should not be a matter for you. And I'm not surprised to see that none of our audience here today have qualified for USAMO or JMO, because if you did, you probably won't be here today with us. You don't need us. But the goal of our program is to have many North-South kids develop the skill and interest and passion to become USAMO and JMO participants, which we have had many in the past, but we wanted to inspire more of the younger generation, kids who perform at a very high level, like top 1% or something like that with AME and AMC 10 or 12 scores, combined scores, are invited to join the Mathematical Olympiad program in the summer, which is the AMO and JMO. So please hang around with us for the next couple of hours. Eric and Shreya will solve the 10 of 15 problems that we didn't get to solve on Friday with Suyash. And Eric will be doing like 2 more 3, so he'll be going like solving problems 2, 5, 8, 11, and 11 plus 3, 14. And Shreya will be doing the rest of the problems when she joins us shortly.
All right, so hopefully you can see my screen. What I'm doing is I'm writing on the iPad, but then it's like supposed to be updating real time on the screen, but there's a little bit of lag. So hopefully nothing goes wrong.
Okay. I don't see anything yet.
Yeah, I haven't written anything yet.
Oh, okay, good.
Okay, so the first question, oh, I mean not first, but question 2 is find the 3-digit positive integer ABC whose representation in base 9 is BCA, where A, B, and C are digits. So ABC in base 10 equals BCA in base 9. All right, so the first thing that we got to do is, because ABC is in base 10 on the left-hand side, we can write this as 100A plus 10B plus C, because that's what it means to write a number in base 10, right? And similarly, in base 9, BCA, that's the same thing as 81, which is 9 squared B plus 9C plus A. All right, and if we rearrange, this equation, then this is equivalent to 99A equals 71B plus 8C. All right, so I subtracted A from both sides. I subtracted 10B, moved it from the left-hand side to the right-hand side. All right, so we're left with this equation, and we want to solve this for digits A, B, and C. So, all right, well, what I did during the test was, you know that A can't be 2-bit. Well, first of all, A has to be less than 9. So there aren't that many A's to check. So you can, I feel like the best way to do this is just to check A one by one. So if you check A equals 1, let's say A equals 1. Now, it turns out this doesn't work, because then you'll have the equation 99 equals 71B plus 8C, and there are no solutions to this, right? Because 99 itself is not divisible by 8, so B cannot be 0. On the other hand, if B equals 1, then you'll have 99 equals 71 plus 8C, which means that 8C equals 28, and 28 isn't divisible by 8. And if B is 2, then, well, the right-hand side will already be greater than the left-hand side, so that doesn't work. So in other words, A equals 1 does not work. So let's try A equals 2. All right, well, if A equals 2, then 99 times 2 is 198. That equals 71B plus 8C. All right, well, 198 is not divisible by 8, so B is not equal to 0. You will find that if B is equal to 1, well, if B is equal to 1, then 198 minus 71 is also not divisible by 8. In fact, it's not even even, so that doesn't work. So that leaves us with if B equals 2. And if B equals 2, then we can compute 198 minus 2 times 71 equals 198 minus 142. Equals 142, which equals 56. And 56 is divisible by 8. In particular, C equals 7, and that is our solution. So we have we have A equals 2, B equals 2, and C equals 7. So our number is 227. So I will now move on to question 5.
Eric, before you move on, so if anyone has questions, we can do the same we did on Friday. Since we are a small group here today, you could raise hands, and one of the organizers can unmute you, so that it's easier that way rather than typing questions in the chat. I see a hand raised. Hold on 1 second. Okay, Akshat has a question. Go ahead, Akshat.
Okay, so I don't know about time limits in the AIME. I've never been to the AIME, but would there be like a way to do this that doesn't require as much computation?
Yeah, so that's a good question. First of all, I'll tell you about the time limit. So it's 15 questions with 3 hours, which is an average of 12 minutes per question. So this solution would, well, I think it would fit in, 2 or 3 minutes. It wouldn't take too much computation. In terms of reducing even the amount of computation that we have now, I think this is a rather quick solution. I mean, we only needed to check 2 cases here, A equals 1 and A equals 2. If you try to, it's not the only way to solve this equation, but no matter what you do, you will have to try some B's and C's to see if, the remainder will be divisible by what you want it to be. So for example, if you take mod 8 on both sides, then, well, what will you get? You will get something like, 3A plus B is divisible by 8. And, well, you would still have to check some values of A and B to make sure that that holds. So I don't think there's any way to, like, escape a little bit of computation here. But it's, like, small enough that it's not going to be a huge time investment.
Akshat, sorry, I don't know if I put your hand down or you put your hand down yourself. If you have more questions, just raise your hand again. And I thought I saw another hand raised by Harisha. Hold on, I'm going to unmute you, Harisha. Go ahead.
Which questions are we doing today?
Oh, good question. We did 0 mod 3, I think, with Suyash. So we did questions 1, 4, 7, 10, and 13 with Suyash on Friday. So we are going to do all the other questions today.
Well, wait, 0 mod 3.
No,
No.
9, 12.
I forgot. So Eric, do you know? Well, hold on one second. Why I don't know what questions he did.
Suyash did questions 3, 6, 9, 12, and 15. I will do questions 2, 5, 8, 11, and 14.
There you go. Yep, sorry. I got it wrong. Yep.
Thank you.
Shreya will do the other 5 questions.
Yeah. All right. So
the next one.
All right, so I'll move on to question 5 now, but feel free to ask questions about any of the previous questions should they arise in the process. All right, so the next question, we have this river. Let me draw the river. So hold on. There's this thing, and it's 264 meters wide. And it flows from west to east at a rate of 14 meters per minute. I think that's fine. We'll deal with that condition later. Melanie and Sherry sit at the south bank of the river with Melanie a distance of d meters downstream from Sherry. So what's happening here is Melanie is here and Sherry is here. And the distance between them is d. All right, relative to the water, we have the rates at which they swim, and at the same time they are swimming towards this point on the north bank equidistant from their starting position. So they are aiming for this point x, called x, that satisfies s equals xm. So it's the same distance from both of them on the opposite bank. And it turns out that they arrive at this point simultaneously, and we want to find the distance d between them. Okay, so see, the thing about this problem is we got to keep track of, it's like not a stagnant river, right? So we need to keep track of how the movement of the river influences the motion of these two people swimming. So because the river is only flowing from west to east, so to make that easier, it's going from left to right. What we're going to do is we're going to break the velocity of each swimmer into the x component and the y component. So, right, because the velocity is a vector and it has both components, and the only component that the current is going to influence is in the x direction. So let's say that Sherry has an x component of x1 and a y component of y. Melanie has an x component of y2 and a y component of y as well. Now, do you see why they have the same y component of velocity? They have the same y component because if you denote their midpoint right here, they're going to arrive at this midpoint at the same time, because x is equidistant from s and n. So the y components of their velocities must be the same. Sorry, that's not the y component is going to be the same because they're arriving at the bank on the opposite side, and that component isn't influenced by the current. All right. And furthermore, you know that x1 squared plus y1 squared equals what is Sherry's rate? What is it, 60? Yeah, it's 60 squared, and Melanie's equation is 80 squared. Okay. Now you also have the following relationship between x1 and x2. Now, and this is where we take into account the current. We know that x1 minus x1, because Sherry is the slower one, so she's the one that's moving with the current. x1 plus 14, which is the speed of the current, equals x2 minus 14. All right, so just like take a moment to process this. This is because Melanie is swimming against the current because she's swimming this way, and the current is going opposite to that direction because the current, I'll make it this color, is like going this way. This is your current, right? So she's swimming against the current. That's why we're subtracting 14 from her x component of velocity, whereas Sherry is swimming this way. So she's swimming, the current is actually helping her go to x. So we're going to add 14 to her x component of velocity. And since they arrive at the point x at the same time, their x components must be equal. Right? Okay. So, all right, cool. Now notice that given these two equations up there, we can subtract them. In particular, we have x2 squared minus x1 squared equals 80 squared minus 60 squared, and that is equal to, so 80 squared is 64 and 60 squared is 60 squared is 36, so you're going to end up with 2800. And well, we can also deal with this equation right here and rearrange it a little bit to get x2 minus x1 equals 28. Right? So we now have these two. And well, x2 squared minus x1 squared, this guy is just x2 plus x1 times x2 minus x1 using the difference of squares. That equals 2800. And look, we can divide. I mean, we already know that x2 minus x1 is 28. That's from this equation right here. So that means that gives us that x2 plus x1 equals 2800 divided by 28, which is just 100. All right, so now we have a really nice system of linear equations. x2 minus x1 equals 28, while x2 plus x1 equals 100. And from these two equations, you can add them together to get 2x2 equals 128, which means x2 equals 64. So x2 equals 64, and therefore x1 equals 100 minus 64, which is 36. All right, and from here you can also solve for y, right? Because you can plug these two values back into this equation. I mean, you can plug in either of them, it doesn't really matter, and I will spare you the computation. I probably have y written down somewhere. Yeah, okay, so y equals 48. I mean, because you already know x1, so say you can take this first guy and say like y squared equals 3600 minus x1 squared, and then take the square root of that, and you get 48. All right, Cool. So that's why. Now, well, what did we need to find originally, right? We needed to find this distance between them. So how do we find the distance between them? Well, let's actually call d, lowercase d, half the distance between them. And we remind ourselves that at the end, we're going to have to compute big D equals 2 times small d. So how do we compute this length? Well, the key now is that we don't, like, the only information we have now that we haven't used yet is the fact that they'll arrive at X at the same time, and at that time, their Y coordinate will be aligned at that midpoint. So we're actually going to use the fact that they arrive at the same time. So if we denote by t the amount of time that it takes for both of them to reach the point X, let's see, t equals time to reach the opposite bank, then how do we find t? Well, we know that the y distance they travel is 264. That's the width of the river. And we know that both of their y components are 48 of velocity. The y components of velocity are 48, which means that 48 times this time equals 2800. And you can compute from here that, wait, what am I writing? Not 2800, equals 264. And you get the t equals, what is it? 11 over 2. Okay, cool. Yeah, you can just divide the two. All right. Well, now it's really easy to compute d, because then you can go back to the x component of velocity, and we have that small d equals t, which is 11 over 2, times the x times their shared x component, which is x1 plus 14. I'll circle that here. Or x2 minus 14, both of which are 50. And that equals, like, yeah, whatever that equals. And then, well, we're not actually looking for this number, but we're looking for 2 times this number. So the answer is 11 times 50, or 550, which is the answer. All right, so I just have a few comments about this question. I mean, okay, so this question was pretty hard for its position. So I won't blame you if you like have a lot of questions about what I just did. Also, I was very surprised to see this like show up on the AIME, considering that this is a question. It's under this category called like relative velocity, which is a topic that you typically cover in physics. So like this technique of breaking the velocity vectors of the two swimmers into the x and y components is like something that you learn in physics. And honestly, if I weren't taking physics, I wouldn't have been able to solve this problem. So I find it very strange that this is on the AIME. This could be like on the AP test, but I don't see it being a math problem. So yeah, in that regard, like kind of strange. So yeah, if you have questions. Otherwise, I'll move on to question 8, which is considerably easier. Actually, the rest of them are as well. So,
Eric, someone has just raised their hand. Just give me a second. Sumant, you're unmuted. Go ahead.
Hi, so I wanted to ask, like, what do you, so in like the second to last step, when you get d equals 11 halves times 50, where'd you get that from?
yeah, so, all right. So the 11 halves, that's the time. So that entire time is 11 halves. So time times the speed, right? So the speed is the x component of the speed, which is what I circled here in green. The x1 plus 14 equals x2 minus 14. We already solved that x1 and x2 are 36 and 64. So x1 plus 14 and x2 minus 14 are both 50. And what this 50 represents is the x component of these swimmers relative to like a fixed point. So not relative to the current, because the current is moving.
Okay. Yeah.
So like, yeah.
Okay. Yeah. That makes sense.
All right, cool.
I don't see any other questions or hands raised, Eric, so maybe we can move forward.
All right, sounds good. Okay, so for this next question, question 8, I'll let you read the question, and I will also, I actually have a diagram drawn here, so I'll share my screen. Here, you can see it, right? Okay.
Yeah, we can see the diagram. Yep.
All right. So, okay. I mean, clearly during the AIME you can't use GeoGebra, but I'm just drawing it here because I think you'll get confused if I draw like really bad looking circles. So, sorry. All right. So here's what the picture looks like. And yeah, so you've basically got these 3 circles in here that are tangent to each of the sides of the equilateral triangle and tangent to the circumcircle of the equilateral triangle. And what we want to do is we want to find the area of this small equilateral triangle in here. That's the one we're looking for. Okay, now I want to make a few preliminary observations here, and that is the fact that if you look at the tangency points of each of these tangent circles, like for example I and F here, you will notice that according to GeoGebra, it appears as if the center O, which I denote as the circumcenter of the triangle, lies on this segment. So this fact is generally true, and we will use this fact in solving this problem. So let me actually first, yeah, so like you got to know this fact, I think, in order to solve this problem. I mean, it's kind of strange that they would put, yeah, anyway, I'll prove this for you right now. So this circle that is tangent, so let's go back to my drawing. I'll prove a general fact for you, is that if you have, say we have a circle, and a triangle inside, not necessarily equilateral, called ABC. All right, and I'm gonna draw this circle that is tangent to 2 sides of the triangle, there we go, and to the circumcircle. This circle has a name, it's called a mixed linear circle. Mixed linear in circle. So there are 3 of them. This one would be the A mixed linear in circle because it's the one opposite to the vertex A. Let's say it's tangent to the circle at T and to the 2 sides at, well, let's say U and V. All right, and what I'm going to prove is that if we draw the in circle, the in center of triangle ABC, the in center, which is the center of the inscribed circle, then it turns out that the in center I lies on the chord UV and is in fact the midpoint of it. Well, actually, if we prove that I lies on UV, then it's obvious that it's the midpoint because, you know, AI bisects this angle, and we know that, right, and we know that AU equals AV because they are both tangents to the circle, which means that AUI is congruent to AVI, which means that UI equals VI, right? So we just need to show that I lies on UV. And well, I mean, to do this, we'll do the following. We'll make the following observation, which is that if you consider the point at which TU meets the circumcircle and UV meets the circumcircle, okay, here we'll call this MC and MB, then it turns out that MC and MB are midpoints of the arcs AB and AC. are arc midpoints. Okay, just take my word for it for now. We'll come back to this fact. So they're arc midpoints, which means that, that means that BI and MB are collinear, as well as CI and MC. So this implies that BI and B collinear and CI and C. All right, and now the fact that U, I, and V are collinear follows from Pascal's theorem. Right, like you see that all right, so it follows from Pascal's theorem on well, I'll just like kind of highlight it. It's like you have this guy and this guy, as well as this guy intersect with this guy, and this guy intersect with this guy. So you can see your hexagon there. So U, I, V collinear from Pascal. Okay, so yeah, so this is a well-known fact about mixed linear in circles, but it's only well known if you've seen it, which is often the case when people cite things as well known. No, but yeah, so we'll come back to this fact, but we will use this when solving the AIME problem. So going back to the diagram here, that's why O lies on the chord joining the two tangency points, because since ABC is equilateral, O, the circumcenter, is also the incenter of ABC, and in this specific case, right? So that's why O lies on that segment. All right, and I'd also like to point your attention to the following. It's that if you do this, then K, which we denote as one of the vertices of the equilateral triangle, then K lies on the ray BO, and that's just due to symmetry. Like that's due to the same reason that like J lies on AO. It's just because like just by symmetry they do. All right, so if you take that, what this means is that we can like redefine the points L and K. I'll rename them to points like other than L and K later, but like we can redefine these as the intersection of BO with this mixed linear circle, and the same thing with L. So, all right, so let's go back to the drawing, and I'll now return to the AIME problem. So, okay, let me erase what I have so far. All right, so basically what we have is there's this circle with an equilateral triangle in it, and we no longer have to draw all three circles because we've redefined the points. So there's ABC and the center O. And we already know that these are the two tangency points, which let's call U and V, like we did before. And so there's this circle, right? So there's this circle, and it's like it touches the circle at T, and let's say the center of the circle is like P or something. Yeah, P. And what did we discover? By symmetry, we discovered that if you extend BO and CO to meet this mixed linear circle again, let's say at X and Y, then X and Y are two of the vertices of the equilateral triangle. And what we're going to do is we're going to find the length of OX, which is also equal to the length of OY, because look, if you go back to the diagram, look, where's the circumcenter of this equilateral triangle that we're interested in? Well, by symmetry, the circumcenter is O. So if we find the circumradius, then knowing that it's equilateral will allow us to find the side length automatically, right? So it's easier just to find O, in this case, OX. Okay, so let's try to make some observations about this diagram. All right, well, first of all, since due to the tangency, we know that this is a 90 degree, these are 90-degree angles. And furthermore, we know that this is 30 degrees here because BO bisects ABC, and same thing here. And well, we know that this is 60 degrees up here because UV is parallel to BC because it's equilateral. And we also know that as a result, this is 30 degrees, that since they must sum up to 90 degrees. And obviously we know that these like line on line. All right, so now what I'm going to do is I'm going to isolate the relevant part of the diagram since we have all the angles figured out. So this red circle corresponds to the red circle that I drew just in the other diagram. So P is here. Again, these are the same points. I'm just isolating this part of the diagram so that it's easier for us to do work on it. And let's say O is here. Right. Now, where are X and Y? So where are X and Y? Well, we know that the angle here is 30 degrees because like this guy is 90 degrees and sorry, because like this like BOX is bisected by OU. So this is 30 degrees, which means that it's actually parallel to UP. We're going to draw this. All right. Now, the one piece of information that we know is that OT is 18. We know the circumradius of ABC is 18. And from there, we can deduce that because this triangle here is a 30, 60, 90 triangle, so we can deduce that this is 12. This is 6. I mean, basically what you do is like, let's say we set this equal to R, then you know that this must also be equal to R, and you know this is R over 2. So you can say like R plus R over 2 equals 18, which means that R equals 12. Right, so we know that this is 12, and we know some of these side lengths like 6 root 3, and this is also 12, and this is 6 root 3, and well, this is X and Y. All right, so now how do we find, and we know that this is 30 degrees. All right, so how do we find OY now? Well, you know that this has length 6, and you know that PY has length 12 because that's just the radius of this red circle. And you know the angle POY because that's 90 degrees plus 30, which is 120. So if we isolate POY, then it looks like this. Right, do you see that? This is 120 degrees. PO is 6. OY is what we don't know, like X, and PY is 12. So we can use law of cosines. Have that X squared plus 6 squared minus 2 times 6 times X times cosine of 120 equals 12 squared. So cosine of 120 is negative 1/2, so it cancels out with the minus 2, and we get X squared plus 6X equals 144 minus 36, which is 108, which means that X, and we can complete the square to get X plus 3 equals 108 plus 9, which is 117, and that's also equal to 9 times 13. So that means that X equals 3 root 13 minus 3. And from there, we can calculate the desired side length of the equilateral triangle, right? Because if we like isolate the desired equilateral triangle now, I'll draw it like up here because everybody knows it. So here's the equilateral triangle. Here's X, Y, and like let's say the third vertex of the equilateral triangle is Z. Well, we know that the radius of this circle is X, like this X that we just determined here. So we can use the fact that this is 60 degrees to get that xy equals 2 times r root 3. So it's actually just 3 root 13 minus, just because of the 30, 60, 90 triangle we can see here. So times root 3, and yeah, you can get the answer from that. It's like in the form like root m minus root n or something, and you can simplify it. All right. So okay, so I guess there are a few key points in this problem, which was definitely the property about mixed linear incircles, that you had to know that O lies on this segment UV. And I guess in general, if when you're taking the AIME and like the problem requires like some knowledge that you don't like, I don't know if you were like familiar with the result before or not, but like if you weren't, like don't take that as a discouragement, but rather like take it as an opportunity to learn something new. So yeah, and also I would recommend you to like read about mixed linear incircles in general, because they are it's a very beautiful geometric object, and they have a lot of properties in general. So yeah, they're really cool. Oh, and actually another thing was like, you notice that there were several times when I like drew the diagram, but then I like isolated a particular part of the diagram. I think this is in general a good geometric strategy to have, because I mean, look, the original diagram was just a mess, right? With like 3 circles. There's no way you can keep track of everything, and you're definitely gonna like mislabel something, or at worst just like you don't know what to do because it's too messy. So in situations like that, you gotta try to get rid of as many structures as possible and make your diagram as simple as possible. For example, we redefined these points x and y, which were 2 vertices of the desired equilateral triangle that we were trying to like figure out the side lengths of. And we saw that by redefining it as the intersection of BO and CO with the mixed linear incircle, we no longer needed the other 2 circles, so we erased them. There was no need to like keep them in the diagram if they were just going to clutter things. And then after we did some angle chasing on this diagram, we noticed that we no longer need the vertices of ABC. Like we no longer need them because they were no longer relevant to our computations. So we isolated the mixed linear incircle. We took this guy and we just copied it over here and erased everything else. Right, and then we kind of did the same thing with triangle POY, where we're like, okay, we need to compute OY, and we have 3 parts of the triangle that we know, which means that we should be able to determine it, and we use law of cosines on that. And there was no need to keep, the other parts of the diagram. So I guess there's this iterative process in, when you're doing computation, especially with a difficult diagram to begin with. I know that the statement of the problem deterred a lot of contestants from solving it because it was so complicated. But this is one of the ways that you can deal with a complicated diagram by iteratively reducing its complexity by deleting structures that become irrelevant once you redefine the points in the problem in a better way. So yeah. All right, so that's it for this question.
That was excellent, Eric. I couldn't follow after first few seconds, but I'm sure our attendees were able to follow. I don't see any questions or hands raised. We can give them. So if anyone has any questions, please feel free to raise your hand. This was a complex problem, and Eric did a wonderful job explaining it thoroughly and giving us some tips as well.
Yeah, I would say, yeah, the beginning of a problem with like this property of mixed linear incircles, I mean, yeah, it's difficult to explain every problem on the AIME like in a self-contained manner. There's always going to be like some theorem that I need to refer to. And like, look, maybe you didn't know what Pascal's theorem was either. So you're like, what are you doing in that proof? And you were like not following it all. And like, yeah, I get that. And it's, it's difficult to like circumvent these sort of issues. And that's just because, for the AIME, there's like a broader set of theory that is needed. And the advice that I gave before stands, just like don't let that discourage you, but in fact, but rather, let that be an opportunity to, learn something new in geometry. All right. So let's move on to question 11.
Let someone raise hand. Just give me a second. Kalpana, I am unable to unmute you. Are you able to unmute yourself?
Yeah, I was gonna ask, are scientific calculators allowed in the AME?
No.
And there's a question in the question chat. What geometry figure does he refer to? I'm not sure exactly.
Yeah, so I was referring to this object called a mixed linear incircle. I'll write it at the bottom of the page here. So a mixed linear incircle is a circle that's, it doesn't have to be in an equilateral triangle. In general, it's a circle that's tangent to two sides of the triangle and to its circumcircle. And it has a bunch of nice properties. So,
Okay.
yeah.
Okay, I don't see any more questions about this question. So whenever you're ready, we can move to the next problem, Eric.
All right, awesome. So this next problem is about a parallelogram and a circle inscribed in it. So we've got this parallelogram. ABCD, and it's got a circle tangent to three of its sides like this. And what happens is there's this chord, there's the secant line AC, hold on, AC, the diagonal of the parallelogram, and it intersects the circle at 2 points P and Q, and P and Q cut the segment AC into three segments of length 3, 9, and 16. And the question is, what's the question again? It's find the area of the parallelogram. Yeah. Okay, so now what's the first thing you think of when you see like these lengths of chords of circles and tangents? You think of PowerPoint, okay, or you should think of PowerPoint. So let's first do some labeling here. Let's call this E, F, and G, I guess. So by power of point of A with respect to this circle, by the way, let me just give this circle a name. Give the circle a name. Let's call it omega. All right, so by power of A, I won't write power, sure, whatever. Power of A, you get that AP times AQ equals AE squared. And from here we get that AE equals, so let's see, AP is 3 and AQ is 12, so AP times AQ is 36, so A equals 6. And AF also equals 6. Remember, equal, if you have two tangents to a circle, they have equal length. That's an important fact. So A equals AF both equals 6 by power of point. And now, if we consider the power of C, then we get that CQ times CP equals CG squared, which means that CG equals what? Well, CQ is 16 and CP is 25. So the square root of that is 4 times 5, which is 20. So CG is 20. Yeah. All right, so now what? Well, I'm going to assign variables in the following way. I'll let X equal BG. And if, well, if X equals BG, then by equal tangents, we also know that BF equals X. And there's some stray marks here. And since the opposite sides of the parallelogram are congruent, we know that BC equals AD, so ED is X plus 14, because both BC and AD have to have length X plus 20, right? And similarly, CD is X plus 6, because we know that BF equals X and FA equals 6. Okay, so now we've basically got the parallelogram parameterized by one variable. All we need to do is find X, and then we will be able to uniquely determine the parallelogram, and from there compute the area. In fact, if I gave you a value of X now, you'd be able to find the area really easily, because you could use Heron's formula to find the area of ACD, the triangle ACD, right? Because you know all three sides of it, and you can use Heron's, and you multiply by 2 to find the area of the entire parallelogram. You see that? So that's going to be our game plan. We're going to find X, and we're going to use Heron to finish the problem. Now the question is, how do we find X? Okay, so here's how I did it during the test. It's a little different than how everyone else, or how the solutions on AOPS look like. We're going to define the following function. All right. So this function f is going to go from the plane to a real number, and it's going to be defined as follows. F of a point x equals the quantity xa squared minus the power of x with respect to the red circle omega. All right. Now, why do I define the function this way? Is because this function is linear. All right. So the question is, why is it linear? Why is it linear? Let's see. Like, do you want to think about it, or? See, if you write it in terms of coordinates, if you write x as like x comma y, then xa squared is going to be something like x minus something squared plus y minus something squared. And the power of x with respect to a circle, you know, also has the form x minus something squared plus y minus something squared. And then there's like this radius squared. That's the power formula, right? And then you see that these x squared and y squareds are going to cancel out. So there are no x's and y's. There are no x squared. There are no quadratic terms in this expression. It's only going to be like some constant times x plus some constant times y, you know, plus maybe another constant. You see that? It's like, think about how this would be expressed in coordinate form. And that's a linear function. So f of x is linear in x. Or why do we care that it's linear? Well, because ABCD is a parallelogram, we know that the vector A plus the vector C equals the vector B plus the vector D. Now, if we take f on both sides and using the linearity property of f, we get that f of A plus f of C equals f of B plus f of D. And we're going to use this equation to solve for x. All right. All right, so let's compute f of A. All right, now f of A, so xa squared, if x equals a is just 0, 0 squared, minus the power of x with respect to the circle, the power of a with respect to the circle, which is just 6 squared. So that's negative 36. All right. Now let's compute c. So, but we'll very similar story here. The power of c with respect to a is ca squared. So that is, well, ca is 28. So that's 28 squared minus the power of c with respect to omega, which is 20 squared. And this is going to be, let's see, it's going to be 8 times 48, which is 384. Okay. All right. So, all right, now let's compute f of b. F of b. All right. So ba squared, that's x plus 6 squared, minus the power of b with respect to omega, which is just x squared. And that is 12x plus 36. And f of d equals the power of d with respect to a, which is x plus 20 squared, minus x plus 14 squared, right? Because that's de squared. And so the x squared, okay, so what is this going to get us? We can get us 6 times 2x plus 34, which is 12x plus 204. All right, so now using this fact, sorry, so f of a plus f of c is 348, and f of d plus f of d equals 24x plus 240. So that means that 24x equals 108. Is that right? that means that x equals 9/2. All right, cool. All right, so x equals 9/2, and all right, so I mean we're basically done now, right? Because all that's left to do is to do Heron's formula, because we've determined x, right? Because this is ACD, and we already know this is 28, and AD is x plus 20, which is like 24.5, and CD is x plus 6, which is 10.5. And well, I mean, I won't. Yeah, so I don't think there's a need to like go through the entire computation here. I mean, you're familiar with Heron's formula, which gives you, which is the following, right? Where S is equal to the semi-perimeter, which is A plus equals C/2. And well, you can plug in the numbers, you can do that. And you will get that the area of this triangle is 147√3/2. I probably don't have room to do the computation anyway, so I'll leave that to you because it is just a relatively straightforward plugging in the numbers. And we're looking for the area of the parallelogram, which is 2 times this. So conveniently, we just need to take the numerator, which is 147√3, and that's the answer. Okay. All right. So let me do some motivational remarks here. Yeah. So I have a feeling that probably many of you might not be familiar with this technique of like defining this linear function. And I agree that it was somewhat of a flashy solution. I was quite proud of it. But I actually think that the official solution, I actually don't know what the official solution was exactly, but I think this is like the essence of the problem. Like, in some ways, the linearity of power over point here is the way to like fully understand the structure of this problem, because there's like this parallelogram and there's this tangents. I feel like this is, it's like the only solution that like, I feel like that's what the problem is about. You know what I mean? So yeah. Like, tell me if you want me to go more into the theory of like linearity and stuff.
Let's give them a few seconds here, Eric, to see if anyone has questions or raising hands. Okay, I don't see any. Oh, hold on one second. There's a new question that as to theory of linearity. Yeah. So I don't know if that means, there was a comment that said the S to theory of linearity. I don't know if that means if they want you to explain more, or they just share the theory of linearity.
What was the question?
So there was a comment as S to theory of linearity. So Kumar
Yes.
and Mary is saying like, do you want more? Yeah, go ahead, Eric.
Okay, sure. Yeah, I'll just tell you a little bit. I mean, okay, let me erase this. So, by the way, I will say first of all that I'll tell you a bit about linearity, but first of all, you would have to be familiar with like power of point, because otherwise, I would say this problem is totally unapproachable if you're like not familiar with power of point. So, let me actually write stuff about power of point first. So if you have a circle with center O, and you have a circle, I won't use P, I'll use like X, then we say that, and let's call the circle omega, then we say define the power of X with respect to omega to be the quantity OX squared minus R squared, where R is the radius of the circle. So if you write this in terms of coordinates, if X is equal to like X comma Y, then the power of X with respect to omega written in terms of coordinates is, so let's say O is like, what do you want to say, like AB or something, then this is like X minus A squared plus Y minus B squared minus R squared. That's a function written in terms of coordinates. So if you subtract So in the function that I defined, I basically like subtracted two of these types of expressions. And what happens when you subtract them, like you can see what happens. Like the x squared and the y squared will cancel out. Like imagine we subtract this minus like a different one, like x minus c squared plus y minus d squared minus another r squared, right? Like the x, you can see that the x's, like the x squared here and the y squared will cancel out, and you'll only be left with linear terms. So what's going to be left is if you use something like power of x with respect to omega 1 minus the power of x with respect to omega 2, if you take the difference between the powers, then you'll get something in terms of like k1x plus k2y plus some other constant k3. And this is linear because x and y are both to the first power, and there aren't any quadratic terms or any strange terms like that. Now, the thing about linearity is all linear functions, and I mean, this is something that you would learn in like linear algebra, but the definition of a linear function is a function that satisfies two properties: additivity. So additivity means that f of x plus f plus y equals f of x plus f of y, where x and y are like whatever inputs. In this case, they are points. So like vectors, so two-dimensional vectors. And it satisfies like this sort of scalar thing. So if lambda is a scalar, then you can factor it out. Now, we didn't actually need the second property in our solution. We just needed this first one. And that's the one that we used. So in particular, we use the fact that when you have a parallelogram, A, B, C, D, then every parallelogram satisfies the property that A plus C equals B plus D. And the way to see this is just like the definition of vector addition. Like this is how you add vectors together. Now, alternatively, you can write like C minus D equals, this is equivalent to C minus D equals B minus A. And well, C minus D, right, is hold on, what is C minus D? That is like this vector. That is this vector. And B minus A, sorry, that's not this vector. It's the opposite one. It's this one. And B minus A is this vector. And they are the same because they are just translations of each other. So you can take f on both sides, and using this first property here, you can get that f of A plus f of C equals f of B plus f of D. So that's the linearity property that we use.
All right, great. Thanks, Eric. Do you think we can move forward to the last question for you?
Yes, we can move forward.
And is
All right.
that question 14, right?
Yeah, question 14. All right, so question 14, we basically got this triangle. ABC, and
Eric, can you put the number at the top, some corner, so that people will know? Okay.
Sure. So yeah, question 14. All right. So a splitting line is a line that splits the triangle into two polygons of equal parameters. And we want to try to find some properties of the splitting line through midpoints. Okay, so let's see. I have the following claim, and I'll tell you shortly why this claim is motivated. Okay, so let's actually start with this midpoint P, called P. And I'm going to draw an angle bisector of this angle A. Now I claim that the line through P parallel to the angle bisector is a splitting line of ABC. In other words, if let's say this intersects at like U or something, then BA plus AU equals UC. All right, the claim this is a splitting line. Okay, so how first, so I guess the first question is like, why is this the case? And the second question is, how did you come up with this? Okay, so I will simultaneously answer these two questions with the following sub-configuration. So there's this really useful lemma that I would recommend knowing. I actually think this lemma appeared on a previous AMC. I think it was on the 2018 AMC. So if you want to look that up, it's like, I think it's like problem, I might be wrong. It's like problem 23 on the AMC 12A or maybe 12B 2018. I don't remember if it's 12A or 12B. Probably 12B. Where it's basically like you've got a triangle ABC and you're gonna choose 2 points X and Y such that BX equals CY. Okay, and you connect X and Y, and the key claim is that if you construct the 2 midpoints of X and Y, so these are midpoints, it's called like M and N, then in fact MN is parallel to the angle bisector of angle A. All right. So let's prove this lemma. And I do think that this is like necessary. Like this fact helped a lot with solving this problem. So yeah, let's prove this. So the proof will be with vectors again. So vectors are really useful. I guess that's the moral with these like 2 geometry problems. Okay, so turns out that vector mn equals 1/2 the sum of vector bx plus the vector cy. Now, this fact is actually not contingent on the fact that bx equals cy. It's just true in general. And I mean, can you like see why this is the case? It's because mn can be rewritten in 2 ways. It can be written as mb plus bx plus xn, and it can also be written as mc plus cy plus yn. So if you add these 2 together, then you can see that mb and mc cancel out because they are of equal magnitude, because m is the midpoint and they're in opposite directions. And similarly, xn and yn cancel out for the same reason. So you're left with bx plus cy, and that's exactly the expression that you have here. All right, so that's a useful lemma to know as well, like a useful sub-lemma. All right, so why does that help us with proving that mn is parallel to the angle bisector? Well, that's because you know that vectors can be translated, and that won't change their that won't change what they are. So you can like say, here's a point x prime, which has equal length. Like x prime is located on AB such that ax prime equals bx, and y is here, y prime is here such that ay prime equals cy, and mn is still 1/2 ax plus ay, but now by symmetry, ax prime plus ay prime is on the angle bisector, like it's here. So that, like by symmetry. So I mean, obviously that means 1/2 of it is also on there. So mn must be parallel to the angle bisector for this reason. Okay, so why does this help us? Well, so we have this lemma, right? This really cool lemma that if you choose 2 points x, y that are like kind of the same distance from their corresponding vertices, like bx equals cy, then the line joining the 2 midpoints is parallel to the angle bisector. Let me rephrase this lemma a little bit. All right, so if we rephrase the lemma in the following way, what if we instead, all right, so let me rephrase it in the following way. It's exactly equivalent, right? So we'll choose 2 points x, y on AB and AC such that xb equals yc. Then the midpoint of xy lies on the line through M parallel to the angle bisector of A. I just said the same thing, right? You would agree that that's exactly the same thing as what we just proved. Okay, let me further restate that by saying, let's say I'm varying point X along the side AB, and Y is varying accordingly such that CY remains equal to BX. So you can imagine like B sliding up AB and Y is like sliding up AC, you know, while maintaining that same length. And I'm going to track the movement of N, the midpoint of XY. Now, as we vary X, N will move along the line through M parallel to the A angle bisector. Right? All I'm doing is restating what we just proved. Okay? Okay. Now, in particular, how about I move X to the following point? I moved X to the point where AB hits this splitting line. Or hit, I mean, we don't know yet that it's a splitting line, so it hits the blue line. Where is Y? Well, Y must be the point. Y must be on AC such that the midpoint of XY lies on the blue line. Right? That's exactly just a restatement of the lemma we just proved. Okay? So where is Y? Well, it must be here. It must be where the line hits AC. Right? Because nowhere else. If we choose like Y here, then the midpoint of XY is going to be somewhere off the blue line. So it can't be there. It's got to be on the blue line again. You see that? That's the only possible way. But according to our lemma, what do we know? We know that BX equals CY. Right? Just again, restating the lemma, BX equals CY. Well, we know that AY also equals AX, right? Because, I mean, this triangle is isosceles, like AXY is isosceles, because you have this and you have this, because of the two parallel lines. So that shows that the blue line is a splitting line. See that? That shows that if you choose the line through the midpoint of BC parallel to the angle bisector, it splits ABC into two polygons of equal perimeter. Okay. So let's go back to the problem. So we showed, so actually the problem was asking us to consider the splitting lines through M and N, which were the midpoints of AB and M and AC respectively. But now we know that these lines are just parallel to the B and C angle bisectors respectively. So I'll draw those in. And let them meet at the incenter I. Now, since they're parallel, and look, we're given the angle between these two splitting lines, right? Well, the angle between these two splitting lines is the same as the angle between any two lines parallel to the two. So the angle between them is the same as the angle between BI and CI, which is, we're given to be 30 degrees. And BIC, therefore, must be 150 degrees. Because BIC is the one that's obtuse, right? Like you can see that. Like BIC is always going to be obtuse because BIC I is the incenter, so it's always going to be obtuse. And you can I'll let you do the angle chasing here. We have the following relationship. We have BIC, the angle equals 90 degrees plus angle A over 2. All right, and since BIC equals 150 degrees, we have A equals 120 degrees. Okay, so this is a very important result. Now, since A equals 120 degrees, let's let AC equal B and AB equals C. Then by the law of cosines, we have that B squared plus C squared minus 2 times BC cosine of A, which is 120 degrees, equals BC. And we're given in the problem that BC is 219, which I find to be very unnecessary, but that is what it is. All right, so we know the cosine of 120 is -1/2, which cancels out with the 2. So we get that B squared plus BC plus C squared equals 219. And we're given that BC are integers. So the rest of the problem is solving this Diophantine equation. B squared plus BC plus C squared equals 219 squared in the integers. So I will now erase what is currently on the screen to solve this equation. All right, let me just rewrite it. B squared plus BC plus C squared equals 219 squared. Sure, I'll just write 219 squared. I was gonna abbreviate it or something, but that's fine. All right, so you'll notice that this is a quadratic in, let's say, B. So we'll write it like this: plus C times B plus C squared minus 219 squared equals 0. We'll like write it in the quadratic form, which means that we can use the quadratic formula and say that B equals -C plus or minus the square root of C squared minus 4 times C squared minus 219 squared divided by 2. And simplifying this a little, this is -C. Well, we can discard the plus, or sorry, the minus, because B is not negative. Plus root of, let's see, 4 times 219 squared minus 3 times C squared over 2. All right. Now, look at what we have here. Since B must be an integer, we know that at least the stuff inside the square root, under the square root, must be an integer, right? Sorry, the square root must be an integer, which means that the stuff under the square root must be the square of an integer. So let's call that square A. So we know that 4 times 219 minus 3C squared, taking this, that must equal the square of some integer called A. All right, so rearranging this, we get that 4 times 219 squared equals A squared plus 3C squared. Okay, so well, what can we do first? Let's make a few simplifying observations. So first, notice that 219 is divisible by 3, which means that 219 squared is divisible by 9. So the entire left-hand side is divisible by 9, which means that the right-hand side must also be divisible by 9. Right? That means that, well, you can check the, okay, so that means that both A and C must be divisible by 3. Because like 3C squared is divisible by 3. So like if you take the left-hand side minus 3C squared, that's divisible by 3. So A squared must be divisible by 3, which means it's also divisible by 9. So that means A is divisible by 3. And similarly, that means that 3C squared is divisible by 9. So C squared is divisible by 3, and therefore C squared is also divisible by 9. So C is divisible by 3. All right, so we have that. Let's define A1 to be A over 3, and C1, define it to be C over 3. And then we can, let's simplify this. So that means A squared equals, let's just rewrite this in terms of our A1 and C1. So A squared is 9 times A1 squared, and 3C squared is 27 times C1 squared. Yes. Okay. And then we can, yeah, and then we can like divide both sides by 9. This is one I really wish I'd written down. Okay, so we get C1 squared with A1 squared equals 146 squared. So, okay, and then we know that like 146 is divisible by 4. So we can in fact say like C2 equals C1 over 2, and A2 define that to be A1 over 2. And then we can divide both sides by 4 again. So we get that A2 squared plus C2 squared equals 142, which is 73 squared. Okay, and then so it amounts to solving this Pythagorean thing, which is honestly like I'm kind of reluctant with like showing even the number theory part of this problem, because I feel like the coolest part of the problem is the geometry part, but I'll just like skim through it. I don't think it's like very necessary to do, but like in general, when you're solving the equation, I'll just rewrite it here. So when you're solving the equation a squared plus b squared equals c squared, then the general solution for this is you have c equals, you can parameterize it in the following way. You like given m and n, you can write a equals 2mn, b equals m squared minus n squared, and c equals m squared plus n squared. So you can use this to solve the equations that we had before, which was like something squared plus something squared equals 73 squared, because 73 equals 8 squared plus 3 squared, right? 64 plus 1. Yeah, you can solve this for, so you can let m equals 8 and n equals 3, and then you can plug them back into the equations that you had, and you can solve for the two integer sides. And it turns out that this is unique, so you won't have like two solutions for B and C, which makes sense. Okay, so yeah, that was the number theory part. But I think obviously don't like pay attention too much about that. Like it was mainly about that cool geometry lemma with, you know, with like x and y on both sides of the triangle. So I actually want to like go back to that and tell you some like additional cool properties of this that are nice to know. I mean, I don't think you'll like ever need them for the AIME, but like it's just cool. So if you have this triangle, sorry, this triangle ABC, and here's just an additional property. If you have the midpoint M, we already showed that the splitting line is parallel to the angle bisector, so it looks like this, right? That's the splitting line. Well, you can also show that this line passes through the following. If you take the medial triangle, okay, it's not going to look like it in my badly drawn picture, but if you draw the medial triangle, which is M and P, where M and P are the midpoints of the sides of ABC, then, and you draw the center of the inscribed circle of this, let's call it S, because we'll reserve I for the incenter. It's called S. S is the center, what happened? All right, so S is the center of the incircle of the medial triangle. Then it turns out that the splitting line passes through the incenter there. And this property follows directly from the fact that it's parallel to the angle bisector of ABC. Because since it's parallel to the angle bisector of ABC, it also bisects the angle PMN, because MP is parallel to AC and MN is parallel to AB. So this property just follows directly. Now, an interesting property of the point S is that an interesting property of the point S is that if you consider if you have a wire, okay, so like imagine you have a wire of I'll draw the wire here. So you have a wire, and this has length, let's say A plus B plus C, okay? And what you do is you fold this wire, so you like bend it, so you turn this into a triangle of side lengths A, B, and C. All right, so you have a wire of this particular length, and then you like fold it, so it becomes a triangle. And it turns out that S, this point S, is the center of mass of this wire triangle, which is pretty cool, right? And I mean, actually, the proof is not hard, because if you want to find the center of mass of this triangle, then you know from your physics class that you can replace each of the sides of the triangle with a point mass at their midpoint whose masses are in the same ratio A to B to C. And you know and therefore from the angle bisector theorem, you will be able to deduce that the center of mass of these 3 point charges must be, not point charges, point masses must be the incenter of this triangle. Because also in their center coordinates, the incenter has this because of the angle bisector theorem. And yeah, so this point S is called the speaker center of ABC. And yeah, it has the property that if you draw a line from the speaker center to the midpoints of each of the sides, then those will be splitting lines of the triangle. The splitting lines are also called cleavers. Usually that's what it's called. So yeah, so these are some additional properties of the geometric configuration this problem is concerned with, which is pretty cool to know. So yeah, that's it.
Thanks, Eric, for the 5 problems. Am I free to start?
Hi, Shreya.
Questions and answers, right? For those.
Yeah.
Yeah.
Does anyone have any questions? You can raise hands. I don't see any question on the chat at this time. I don't see any raised hands too. Eric, that was wonderful. Thank you very much. I really appreciate your time. We all do. It was great having you for the AIME Prep Club webinar too. The Prep Club workshop. We'll keep in touch. Good luck with all your endeavors, and feel free to stay if you have time, or if you have to leave. We understand. It's up to you. Alrighty.
Yes.
Do we all need a 5-minute break, like stretching and getting some water, or at least just not thinking about math for 5 minutes, maybe? What do you think, Vinay? Should we do that?
I guess 1.5 hours, right? So yeah, maybe 5 minutes. So 7:45.
Yeah. So Shreya, if you could share your screen and put have a plain Word document and say we're on a short break. See you at 7:45 Eastern. That way,
yeah,
something like that, so that if people know. Are you a presenter now? Can you share screen?
I don't think I can share. So
Yeah,
the version of me that's not talking about that.
Yeah.
No, not this one. The other one.
Oh, the other one. Okay.
The one that's here, not the one that's offline. The one that's here.
Okay, yeah. We'll make you present.
I made you a presenter, Shreya.
Daisy, Shreya is logged in 2 devices.
Okay. There is another one, right?
Yeah, is it good now, Shreya?
I think so.
Okay.
Yeah, I'll try and get this working.
Yeah.
I'll also pass the recording now. Please remind me when we start, okay?
Yep.
Okay.
Should I get started?
Okay, I just started recording, so you can go ahead.
Okay.
Oh,
awesome.
Shreya, let me give a brief introduction about who you are and how thankful we are to have you.
Yeah, definitely.
Hi, everyone. Shreya Magaluthu has always been interested in problem solving and has enjoyed participating in NorthSouth contests since 2nd grade. She won 3rd place in Senior Science B in the NorthSouth Nationals at UMCP. She participates in high school math, computer science, and science competitions, including Science Olympiad. She received the MIT's Philosophy Award for the papers she submitted for the course Paradox and Infinity. She is looking forward to joining MIT this August as a computer science and math major. I've had the honor and privilege to work with Shreya over the last few months as she volunteered to coach our AIME Prep Club, that ran for several weeks between October and February this year for NorthSouth. She did an excellent job with Eric and Suyash, and I'm very thankful for her time here again today to go over the last 5 questions of AIME. And I apologize, the handouts that we submitted for AIME questions, some of the questions didn't come out right when I copy pasted it from online. So I had just sent a link that will take you to the Art of Problem Solving's website that has a 2022 AIME 1 problem list. So if you don't have the correct problem list, please look at the chat and click on that link, or Google Art of Problem Solving in 2022 AIME 1. That should take you to those questions.
I think the Word document looks good, Priya. The Word document looks good.
PDF doesn't look good then?
Yeah, PDF doesn't look good, but Word is
okay. Good. Oh, that's good to know. So use the Word document and or click on the link. So one of them should work. Thank you, Shreya. You can go ahead and get started so that we can finish on time, hopefully.
Okay, sounds good. Yeah, these ones should be relatively quicker. I wanted to ask, so if I want to ask, so should I ask questions or should I just do the problems? And then they will ask me questions after.
Yeah. We only have 35 attendees. So if you want to ask questions, and we can wait a few seconds and see if someone raises hands.
Okay.
And we can unmute them.
Okay, so is there a place that I could like read what they're saying, like the chat or something, or?
They can put it on the question chat. Daisy Uncle, can they put it on chat?
Yeah, I will say, make it as a which one? Organizer. Which one I should do? The one you are right now on?
Yeah, the one I'm talking right now.
Okay, you're an organizer now. See whether you can do it.
Yeah.
So you have that. You have the question tab.
Yeah, I can see.
See the questions tab come up. Okay, perfect.
Yeah, okay. If they put questions there, you can see that Shreya, but we can also unmute them because it's a relatively small group compared to AMC 8 or AMC 10 sessions.
Yeah, you can detach the tab to a bigger screen if you want.
Sorry?
That the questions tab, you can detach it for a bigger screen so you can read it clearly.
Okay, sounds good. Thanks. Yeah. Okay, good then. So should we start? Okay, awesome. So this is problem number 1, the 11th problem you'll be doing in this series. Okay, so quadratic polynomials p of x and q of x have leading coefficients 2 and -2 respectively. The graphs of both polynomials pass through the points 1654 and 2053. Find p of 0 plus q of 0. Okay, so we have quadratic polynomials. Something that we can do is write it in standard form. So we can say p of x is ax squared plus bx plus c, and q of x is like dx squared plus ex plus f. Okay. So I'm gonna ask a lot of questions. If it takes too long for you guys to answer, I'll just like say it myself because I know it might take a while to type. Given these two equations, what are we trying to find? Like what's p of 0 plus q of 0? Okay, good. So it's c plus f, right? Okay, awesome. So at this point, what we might like to do is fill in what we know. So for example, we know that a is just 2, and b and d is -2. And what we will notice is that we want something that is like a sum, so like c plus f. If we take the sum of both p of x and q of x together, we manage to cancel out the quadratic terms. So let's call this new function like d of x for difference. And this will just become, okay, yes. So someone said R of X. That will work too, I guess. But I will just say, okay, so I guess you said PQR. I said PQD because D is difference. Okay, anyway, we'll have B plus E times X plus C plus F. So this is a new function that we get. And so at this point, we have 2 points and a linear equation. So we can definitely find these 2 constants. And specifically, we want to find the second constant. Okay, so let's just plug it in. What is D of 16? Well, that's 0. Because both of them are the same at 16. But yeah, in particular, we get B plus E times 16 plus C plus F is 0. And then for 20, where's the chat where you can answer? That's just the question and answer chat. So the one that you're typing in right now. Okay. So then we get B plus C times 20 plus C plus F is also 0. Okay, so at this point, what should we do? Actually, this does not make much sense. Sorry. Give me a second. Okay, I will back up a second. We can first plug in the given points into P of X and Q of X and then subtract, and then it will make more sense. Okay, so we have that P of 16 is 2, I'm just going to say 16 squared, plus B of 16, B times 16 plus C, and Q of 16 is negative 2 times 16 squared plus 54. And okay, plus E times 16 plus F is 53. Okay, and then P of 20 is 2 of 20 times 20 squared, B of 20, C, D, sorry. Okay, good. Okay, I understand what the typo that I made last time. So in this case, D of X will be P of X plus Q of X instead of the difference. So I will say like A of X. And now it becomes better because at this point we get, this is B plus E times X plus C plus F. And then when we go into plug in A of 16, instead of getting like 0, we'll get 108. And A of 20 will be 53 times 2, which is 106. Okay, good. Then we can say that this is, okay, B plus E times 16 plus C plus F. And this one will be B plus E times 20 plus C plus F. Okay, yes, I did not scroll down in the question and answer, and you guys are spot on. Okay, good. Yes, okay. Yeah, okay. Now I think someone said multiply the top equation by 5 and the bottom equation by 4. Sure. If we do this, then we get 20 or 80 times b plus c plus 5 times c plus f is 108 times 5, which is like 540. And then this one will be 80 times b plus c plus 4 times c plus f. And 106 times 4 is something like 424. Yeah, probably. Okay, good. And now we subtract. So we get c plus f is something like 116. Okay, good. Yeah, exactly. And now that's our answer as we determined in the beginning. Okay, good. So if you have any questions on that, that was problem 1. And yeah, I kind of like did not define a of x correctly at the beginning, but I'm glad that we sorted that out. And now we can go on to the next problem. Okay, good. So this is question 4. If you have any questions on the previous problem, just let me know right now. Otherwise, we're going to move on. So let w and z be complex numbers such that w is the square root of 3 plus I over 2, and z is -1 plus I root 3 over 2, where I is the square root of -1. Find the number of ordered pairs r and s of positive integers not exceeding 100 that satisfy the equation I times w to the r is z to the s. Okay, good. So, okay, do W and Z ring any bells to you? Like, do they look familiar? I'll write them out in standard form, actually. Okay, so we can see that root 3 over 2 and 1/2 will give us, okay, so if we like plot it on the unit circle, we get root 3 over 2 here and 1 over 2 here. So this will be 30. So W is cis 30. And in a similar way, if we graph Z, we get -1 on this side and root 3 over 2 on this side. So this is 120 degrees. So Z is cis 120. And I think we covered this when we talked about like complex numbers in the prep club. But when we say like I times W to the R equals Z to the S, we can rewrite this in terms of cis notation. So this is cis 90 times cis 30 to the R is cis 120 to the S. But when you like multiply complex numbers in cis notation, you add the angles. So this becomes 90 plus R times 30 is S times 120. Okay, so cis is just notation for cos 30 degrees plus I sine 30 degrees. So the argument, which is an angle, will just be cos of that angle plus I times sine of the angle. Okay, but yeah, if you have any questions, just feel free to put it in the chat. Okay, so now we're just trying to solve this equation mod 360 degrees, because as soon as you set one of these quantities to be 360 degrees, it's the same as 0 because you go all the way around. Okay, so how do we do this? Also note that we have a restriction that both of them are positive and that they're not more than 100. So those will be key. Okay, so note that S can have like at most 3 distinct values, 0, 1, and 2. And if it's anything other than that, obviously it can't be 0 because like it has to be positive. So we can say 1, 2, and 3, for example. But note that if it's anything other than 1, 2, and 3, we can just simplify s times 120 and get 1, 2, or 3 times 120, and it'll be the exact same thing. Okay, good. So let's take those different cases. So S is like 1 mod 3. In this case, we are trying to solve the equation 90 plus 30R is 120. So if we rearrange, we get 30R is 30. So we know that like one possible solution is R is 1. Note that R like will cycle has cycles of 12, right? So it has only 12 distinct values, 1 through 12. Because if you have like 13, for example, it's going to be the same thing as R is 1. Okay, good. So note that then our possible values for R will be 1 and then 1 plus 12, which is 13 because it gives the same exact answer. And then 13 plus 12, which is 25, all the way up till like 97, which is 12 times 8 plus 1. And so since we went from 0 times 12 plus 1 to 8 times 12 plus 1, we have 9 values here, 9 possible values for R. Okay, good. So we have 9 values for R given that S is 1. And how many ways, or S is like similar to 1, and how many ways can S be similar to 1? Well, S can be similar to 1 when it's 1, or 1 plus 3, which is 4, 7, all the way up to 100. Note that we can say it's similar because we can split it up as long as S is like 1 plus 3 times some integer, we can split up 1 times 3 times that integer times 120 into 120 plus 360 times some integer. So this guy does not matter because it's the same thing as 0, and then we just get 120. So we'll just do things in mod 3 from now on for S and mod 12 from now on for R. Okay, good. So now we take the case when S is similar to 2. Okay, by the way, this is 34 values, I think. So this is 9 times 34 for case 1. Possible values of R and S, like possible pairs for R and S. Okay, now we take S as 2. Note that we can't have 101 because that's bigger than 100. So we're going to add 1 to everything in the first case except for the last one. So we get the last one is like 98. So this is 33 values. Okay, good. Now we have 90 plus 30R is 120 times 2, which is 240. Subtracting 90 on both sides gives us 30R is 150. So we know R has to be similar to 5. And if we go all the way, we realize that we can't have 96 plus 5 because that's 101, which is too big for us. So then we take like 84 plus 5, which is 89. So this is our last value. So we go from 0 times 12 plus 5 to 7 times 12 plus 5. So this is 8 values. And so this case will give us 8 times 33 total. Okay, now we take our last case in which S is similar to 3. Similarly, we can just add 1 to each of these values and get a new possible value of S. This is 3 all the way to 99, which is also 33 values. And then we take 90 plus 30R is 360, which is the same as 0, but we'll just use 360 for now. And then we get 30R is, I can subtract 270. So R is similar to 9. Okay, now we can take, like similarly to last time, we only have 8 values because 84 plus 9 is already like 93. And we can't go any more than that. So we take these 8 values and multiply them by the 33 values for S, and we get 8 times 33. Okay, and then adding them up, which is a bit of like algebra, which you can do. So I'll just write down the 3 numbers and then you can verify them for me, or verify their addition for me if you want. Oops, 33. this will probably be 834 if I didn't do my math wrong. Okay, and you can check that on your own time and then tell me in the chat if you want to. So we'll wait a few seconds if you want to do that, and then we can go to the next problem. This problem wasn't so much like a complex number problem as it was like a number theory problem, like modulus. But you did need to know stuff about, oh, it is 834. Okay, thank you. But yeah, so you did need to know in the beginning a bit about complex numbers, and then the rest was just number theory. Okay. Okay. Sorry. Number 7. Let A, B, C, D, F, G, H, I, D, E, F, G, H, I be distinct integers from 1 to 9. The minimum possible value of A times B times C minus D times E times F over G times H times I can be written as M over N, where N plus N are relatively prime positive integers, find N plus N. So we're trying to partition the integers from 1 to 9 into 3 groups such that this thing is minimized. Okay. Also note that since it says both of them are positive, we want this to be like the smallest positive fraction. So as be as close to 0 as you want to make it. Okay, somebody's asking if we should try limiting the numerator or the denominator. Okay, so which one do you think is harder to limit? And I think by limit you mean like upper bounding this and lower bounding this, like maximizing this and minimizing. Okay, so while you think about which one you might want to try to limit, I'll try and get us situated in that direction. So note that like if you have some number for the top, like ABC minus DEF, and then so say this is like 3 for now, and then you change it to 2 by like changing up which numbers A, B, C, D, E, and F were. Okay, so now you have a smaller numerator, which is good for you. The thing is, you might have increased your denominator by some amount, but as long as you didn't increase it by like more, or you may have decreased your denominator by some amount. As long as you didn't decrease it by a factor of more than like 2/3, you're fine, because then your denominator will be like at least as big, or it will not counteract your efforts to decrease A, B, C, D, and F. Does that make sense? So like, for example, if you change your numerator from 2 to 1, then as long as you didn't like have your denominator, you're fine. Right, exactly. So you're saying the denominator is easier, but then A, B, C, D, E, and F is limited. Exactly. So that's why you want to do the harder one. You want to limit the harder one so that the easier one will just fall into place as you want it to. So we're going to focus on A, B, C, D, E, and F, and then see if that is actually the minimum possible value that we can have. Does that make sense? Okay, let me know if it doesn't make sense. So we'll start by figuring out what kinds of things we can do to A, B, C, D, E, and F. So ideally, we want it to be like, okay, so, before I get to that, relatively prime positive integer just means that the greatest common divisor, so if you have two numbers A and B, if the GCD of A and B is 1, then they're relatively prime. Does that, okay, let me know if that doesn't make sense. So what do we want A, B, C, D, E, and F to, minus D, E, F to be? Ideally, we want this to be 1. So we're trying to find like groups of 3 numbers that subtract to 1. Necessarily, this means that one of them will be necessarily this means that one of them will be even and one of them will be odd. Okay, good. So this will need a little bit of trial and error. Yes, I can repeat that. So if you have 2 numbers, such as like 3 and 4, we know that the greatest common divisor between 3 and 4 is 1. So we can say that they're relatively prime, even though 4 is not prime. So 4, we cannot say that 4 is prime, but it is relatively prime to like 5 or 9. Okay, so yes, so someone says, in terms of what we can use for the odd numbers, or for, so say without loss that DEF is the odd number, then we can use 1, 3, 5, 7, or 9. He's saying that, look, 9 is a pretty big number. Maybe we don't want to sacrifice it for this, so we can leave it for the denominator. Okay, maybe. Okay, good. So we can kind of like write out the 9 numbers from 1 to 9. And okay, so we can like do trial and error. The biggest issue when it comes to finding like differences that become 1 is that if you work on the lower end, it's really hard to get numbers that are close to each other, because like multiplying by 2 versus multiplying by 3 can often make a big difference. Okay, so I'll give you like 30 seconds to think about it, and then I'll tell you what the trial and error will get you in the end. Okay, good. So you might try a lot of things and you might end up with like differences of 3 or something, but actually it is possible to get a difference of 1. So this one will be, I think 7 times 5 times 1, which is 35, and then 3 and 2 and 6, which will be 36. So 36 minus 35 is indeed 1. And then what do we get for the rest? We get 4 and 8 and 9. So does anyone want to really quickly tell me what this multiplies to? Okay, yeah, so whoever said 320 minus 32, that's right. I'll just simplify that for you. So in this case, we get 288. Okay, so this is a pretty small number, which is good for us, but we also don't know at this moment if it's the like minimum possible value, but we can check that pretty easily. Why? We use what we said before when it comes to like decreasing the denominator and getting or decreasing the numerator and figuring out how the denominator is affected. Okay, so what is the like best possible denominator that you can have, or like, yeah, so we want a denominator of like 7 times 8 times 9. All right, but this with this, it's not possible to get, so like if you have 15, so if you use 7 times 8 times 9, the only other odd numbers that you can have are 1 and 3 and 5, and you can pretty easily check that there's no way to get like 16 or 14 using the rest of the evens, right? You can pretty easily check this because you know that you need at least it to at least be divisible by 8, because you aren't using or actually you don't need this. Actually, yeah, because you aren't using 7 and 9, so you need this. You need every even number to be divisible by 8, so 14 is out of the picture, and then you also know that if you only have powers of 2, you need to use 2, 4, and 8, and this multiplies to something that's way larger than 16, so 16 is also out. So it's impossible to get 7 times 8 times 9 and have 1 in the numerator. What's the next best thing? The next best thing is having 2 in the numerator, and then the denominator, the biggest possible value of the denominator will be 7 times 8 times 9. So we know that out of the possible 1 numerators, we're the best. Okay, so we can overrule this guy. And out of the possible 2 numerators, okay, wait, I did not read the chat. So I'm unsure about what like 504 and 720 are. So if you want to, sorry, if you want to clarify this, let me know. Okay, good. But notice that if we have 2 in the numerator, that's equivalent to 1 being in the numerator and then 3.5 being in the denominator. So, and this is necessarily bigger than 1 over 4 times 8 times 9, which is 1 over 288, which is what we got. Oh, you're saying this is 1 over 252? Yeah, so it's bigger. Awesome. 7 times 8 times 9. Okay. So I'm not sure why for 720, I'm not sure why we want to multiply all of the remaining numbers. And yeah, this one is 504 like you said. And then divide by 2 is 252. Why are we doing? Oh, okay, I see. So you're factoring 720 and then getting like the smallest possible. Okay, okay, sure, that works too. I think you can actually don't quote me on this because it's been a while since the AIME and yeah, it's been a while, so I don't know exactly what the outcome of like every single possible trial and error that you could do is, and I'm sure that you can get it very small, even without doing 1 over 228. Like you can probably get it very small with the 2 in the numerator. It just won't be as small as 1 over 288. So you can like experiment with that on your own. Can't I make the numerator 1 and divide? Yes, we can do this. But the reason I said 3.5 here is to directly compare it to 1 over 4 times 8 times 9, which was our answer. Right? So if we get similar values for 8 and 9, so that part hasn't changed, but we know that 4 is bigger than 3.5, we can directly say that our answer is smaller than this. Yeah, so even if you try 6 times 8 times 9, our answer will like necessarily be better because you can't have a 1 up here. So actually, I think you can show that you can't have a 1 up there, but you can try it yourself. Actually, yeah, try it and let me know. Okay, wait, what is 432? If you want, we can like talk. Okay, yeah. If you want, we can talk afterwards about this problem. Do we have any other questions? Sorry?
We don't see anybody raise their hand. There's some in the question chat, right? Do you have them? Why can't the numerator be 1? That's covered, I guess.
Oh, okay, so I scrolled down. The numerator can't be 1 because if you try like other possible values, you can't like create. So first of all, we know that you can only have odd, like you can one of them needs to be composed of only odd numbers. And then once you have that restriction and you try like the different possible values, it's impossible to create like an even number on this side where the numerator is 1 and we have like a sufficiently large denominator to work with.
Okay, cool. I don't understand what type of question this would be used. Can you show and explain? What type of question this is? Hiramani, do you want to unmute and ask your question? I didn't quite get what the question was. I don't understand what type of question this would be. Useful, you mean? Can you show and explain? One second. But it's not letting me unmute. Okay, one second. Hiramani.
You mean like what classification this is? This might be a number theory problem.
Okay. Can you try now, Hiramani?
Can you hear me?
Yes, we
Yeah.
can hear you.
Yeah, my name is actually Isham. Is my
Oh,
parent.
sorry, that's that.
Yeah.
Okay.
Okay. Though I was asking like what type of question could I use this formula for? Like, can you give an example of a question I can use this for?
So what formula?
No, this what you showed now. What like can you give a question? And that would I would need to use this like the yeah, a problem.
So this is a problem that we use this for solution also for, right? So that would be a sample problem.
Okay, then he missed the problem then.
Yeah, I came a little bit late, so I didn't.
Oh, you can view the solution in the video. We'll share the link for today's recording. So tomorrow morning you'll get the link and you can watch it again.
Okay, thank you.
Thank you. Shreya, you can move to the next question.
But this was problem number 7, right, Shreya? For AIME.
Yeah.
Yeah, problem 7, AIME 1, 2022.
No, there are
Okay.
no answers to this. I mean, technically there are, but it's every number from 0 to 999. So, you know, 1,000 choice, multiple choice
Very
question.
funny, Shreya. Yeah, but no, these are not multiple choice questions, right? Yeah.
Yeah,
But
no, they won't.
all answers are like 3-digit answers.
Mhm.
Please go ahead with the next question.
Okay, awesome. Okay. Okay, so number 10. We have 3 spheres, and they have various radii, and they are mutually externally tangent. Generally, these problems tend to be harder to visualize, but I will try drawing spheres. Okay. A plane intersects the spheres in 3 congruent circles centered at A, B, and C. Okay, so we have a plane that is intersecting these spheres. And okay, I will try and use different colors. Oops. Okay, And so it intersects these three circles in these three spheres in three circles. And it so happens that these are congruent circles. So we have A, B, and C as the centers of these circles. And they all lie on the same side of the plane. We also know that this length, A to B, is 560. Okay. Oh, the square of that is 560. And then we want to find AC squared. So that guy. Okay, good. So what can we do? Okay, so the prospect of having three differently sized circles and then having a plane cut them in three congruent circles is a little hard to palliate, but we can make it easier on ourselves by only looking at things that maybe we know how to deal with. So for example, we can look at the centers of the three spheres. Okay, so let's look at one sphere, but squish it so that it's just a circle. So we have the center of the sphere, and then we have the plane, and it cuts it into some circle. So this will be the sphere with radius 11. So we know that this length is 11. And okay, we know that if this is A, and this is the point at which the plane intersects the outer point of the sphere, we know that this length is congruent or is the same for each of the circles. So it'll be something like this. If this is R, then this is R. And if you can imagine a bigger circle, 17, I think, 13, this will also be R. Okay, that's something. So maybe we want to label the distances between, let's call this O sub A. So maybe we want to label the distances between the centers of the spheres and the centers of the congruent circles as A, B, and C. And then we can write the equations. 11 squared minus A squared is R squared using the Pythagorean theorem. So similarly, we can write B squared and C squared. Okay, good. So you wrote some stuff down. Wait, let me. Okay. But this isn't enough for us to actually figure out what's happening. So let's go back up to what we have. We also know that AB squared is 560. Okay. So AB is this guy, which is, our diagram is kind of messy. So let's redraw this. So we have two circles. One with radius 11 and the other with radius 13. And then, so we have some plane. And we have A and B. This is A, this is B. Okay, that's good. What do we know? That this guy squared is 560. Okay, we also know that if you have any chord, the distance from this, or the line, or actually, we already said that we had the midpoint of this chord, or the chord where the plane intersects the sphere. Midpoint of this is A. And we also know that the line from the midpoint of any chord to the center of a circle is perpendicular to the actual chord itself. And you can see this using similar triangles. So you know that this is R, and this is R, and this is the same. And this is the midpoint. So you know that these two triangles have to be congruent by side, or whatever. And then you can say that the angle in between must be 90. Okay, let me erase this. Okay, so using this, we can like kind of shift AB down because it's a rectangle. And so we'll get something here. We know that it can't be a perfect rectangle because these two sides are not the same because this circle is bigger than the other and the radiuses are the same. These two radiuses are the same. So the two sides cannot be equal. So we know it must be like some sort of trapezoid. And so if we shift AB down to the center of this circle, O sub A, we get like a really tiny like right triangle. So let me redraw this for better viewing. So we have this is the right angle. We know that like B is bigger than A because of the sizes of the spheres. We know that this guy is AB. This guy is B minus A. And this guy will be 11 plus 13 because this is the like line that connects O and OB. So this is 24. And we can say that 24 squared minus B minus A squared is 560 using the Pythagorean theorem again. So from this, we get B minus A squared is 16. And since B is bigger than A, we can say that B minus A is 4. Okay, good. So now we can use these two equations to figure out what exactly B and A are. So we get that like 11 plus 13 times 11 minus 13 is probably B squared minus A squared, which is 4 times B plus A. So B plus A must be 24 times, or let me make this 13 minus 11. Okay, that's better. 24 times 2 over 4, which is like 12. So 2B must be 16, so B must be 8. So A must in turn be 4. And then we can plug it back into here so we can find R squared. R squared must be like 11 squared minus A squared, which is like 121 minus 16, which is some number. And we know that R squared is also, is this 19? Okay. Okay. And we know that R squared is also 19 squared, which is like 361 minus C squared. So if we take C squared, it must be 361 minus 121 plus 16, which is like 240 plus 16, which is 256. Okay. And so we know that C must be 16. Okay, and using this, we can pretty quickly find what AC is. So we'll draw a similar diagram. This time, one of the radii is 11 and the other is 19. Okay. And this time we want to find the distance from A to C. Note that this side is 30, right? And this side is C minus A. Let me draw with an arrow so you can see better. This side is C minus A. C minus A is 16 minus 4, which is 12. So AC squared will just be 30 squared minus 12 squared, which is like 42 times 18, which is some number. If you guys want to multiply it, actually, I'll just multiply it. Oh, okay, there are no questions in the chat. No, it's not true. It's 33. Okay. So it's like 756. And that should be our answer. Okay, thanks, Alvin. Do you guys have any questions?
I don't see any raised.
Okay.
Yeah.
Yeah, so I think you probably have seen these kinds of questions or like parts of this question in like different contexts. Like for example, you probably had two externally tangent circles with like some line crossing them. But to have them be put in spheres makes you have to like work to figure out where like how to extract these parts of the problem. And I think that was like the main difficulty in this one. Okay, awesome. If you don't have any questions, we'll go on to the last problem, which is problem 13. Okay, so let S be the set of all rational numbers that can be expressed as a repeating decimal in the form 0.abcd, where abcd is like a 4-digit number, where at least one of the digits a, b, c, or d is non-zero. Let n be the number of distinct numerators obtained when numbers in S are written as fractions in the lowest terms. So then it gives us an example. So we know that 4 is in S because you can find some ABCD such that 4 is the numerator of the fraction. So in this case, it would be like 0.3636 is 4/11, and that's one possible fraction in which 4 is the numerator. And similarly, 410 is the numerator in 0.1230 repeating. Okay, and then we want to find the remainder when n is divided by 1,000. I think I answered your question, Eric. This is the last one. Okay, good. So if you guys need me to like clarify on like what this notation is, feel free to ask. Otherwise, we'll move on to like actually solving the question. Okay, so note that there, like when you find out how to convert repeating decimals into fractions like x over d, where d is the denominator, what you will get is it'll actually just be ABCD over 9,999. And we can derive this, or actually this should not be. When I say ABCD, I mean like the number, not A times B times C times D. Okay, so if you want me to derive this, we can do that. Does A is... So we want the fractions to be in lowest terms. So it can't be like every number over every number. Okay, so I also don't know where you're coming from with the 9999 times 5,000. Yeah, so 1/1 works, but not 3/3. That is correct. Okay, so if you want to let me know about this, I'll read it. Otherwise, and if you want me to go over the derivation of that, I will do that also. Otherwise, we'll just focus on counting the number of numerators that you can have where the denominator is some factor of 9999. So, okay, so we have a couple of cases. One, what if the denominator is actually 9999? Then, so we have some restriction on the numerator. What is the restriction on the numerator? We know that, like, we can't, for example, have 9 over 9999, right? This will not work because 9 is, this number is not, what's it called? A fraction in lowest terms. So we have to take away all numerators that have, like, any common factor with 9999. So every, like, relatively prime number to 9999 that's less than that number itself, we should count it. Okay. Okay, so yes, we want to find all numbers that are coprime to 9999. Okay, so I realized that this is how to find triangular numbers, but I also don't know why we want to find triangular numbers. So yeah, let me know. Okay, so when you want to, okay, so note that because we're looking at every single possible number below 9999 that is co-prime to it, we can use, might be like, okay, so it's some formula, it's probably called like totient function. But intuitively, we take every number that isn't divisible by 9. So, or isn't divisible by 3 because that's the prime number. So that's 1/3 of every number below 9999 is divisible by 3. So we take 1 minus that fraction. And similarly, for every number that's not divisible by 3, 10/11ths of them are not going to be divisible by 11 as well. Note that we're taking 9999 is 3 squared times like 11 times 101. This is the factorization. And you can see this easily by noting that 1111 is 11 times 101. And then the 3 squared comes from the 9s. So, okay, so I don't know what your last comment was. So if you want to clarify why we're looking at numbers without 9999, then yeah, I'll read that. But for now, let's continue finding the number of coframe numbers to 9999 that are below it. So we have just multiplied by the 3 fractions that will like pare down each, pare down the numbers that are relatively prime, or that will take out the numbers that have these prime factors, so that we're just left with numbers without 3, 11, and 101 as factors. Okay, and so you've done the computation for me. Thanks. This is 6,000. Okay, good. So this is the first case in which we have the denominator of 9999. But it could be that we have, like in some other fraction, we have a denominator that is divisible by 3. We just need a numerator that is divisible by 3. We just need, in that case, for the denominator not to be divisible by 3, because then it will work out. So for example, if we have a denominator of 1111, then we are free to use each of the numbers that are divisible by 3 that we took out in this fraction. Note that they still cannot be divisible by 11 or 101. They can only be divisible by 3. And similarly, we can, if we want like numbers that are divisible by 11, we take a denominator of like 9090. And if we want things that are divisible by 101, then we take a denominator of like 99. Okay, are there any? No? Okay. Okay, so in this case, we will just count the number of numbers that are divisible by 3 and not 11 and 101. Similarly, here we take divisible by 11 and not 9 or 101, and here divisible by 101 and not a 9 or 11. Okay. So okay, so we can take probably 1111, and yeah, okay, we can take 1111 and divide it by 3. So an upper bound on the number will be 333. Yeah. Sorry, I'm just thinking. And in this case, we take, sorry, this is 909. 909 over 11, which is
So it should be divisible by 11, right? So multiples of 11 till, so from 11 till 902. Sorry, 11 till 902. So that's 55 multiples of 11, right? For case 3.
sorry?
So 11, so divisible by 11. So those are multiples of 11, right? So starting with 11, 22, 33 until 902.
Yeah.
So I guess 55 values.
Okay. So we can just say that it's 55 values. The issue is we need to remember that like 909, the total number of like numbers that are divisible by 11 from 0 to 909 are 82. And then we pare that down to 55 based on being divisible by 9 and 101. Okay, so I think we can safely say that there are no numbers divisible by both 11 and 101. So the only number that we need to worry about is 9. Okay, or technically 3. So every third number probably will be divisible by 3. So we can take 82 times like 2/3. And then we only need to worry about the 82nd number. Okay, good. So until the 81st number, we can take 2/3, and this will be 54. The 82nd number is also not divisible by 3 because it's 82 times 11. So we're fine, and we get 54 plus 1 is 55. The only issue is 333, which I'm rather concerned about because it's supposed to be 334, and we haven't considered 11 yet.
So since that would be multiples of 9, I guess, right? So
9?
Multiples of 3, yeah. So 3 to 1110. So if we count those, that will be 334, right?
Am I just dividing wrong? Wait.
So if we are counting multiples of 3, so from 3 to 1110, will be the last multiple of 3, right?
Oh, I can't divide. It's not 333. It's 3 70 R1. Okay, good. Now we have room to take out multiples of 11. So note that the last possible multiple of 11 will be like 370 over 11, which is 333. Okay, so 11 times 33 is 343. Okay, so this is the last possible multiple of 3 that's also a multiple of 11. Actually, that's untrue. It should be like 4. 33 times 11 is 373. No, it's not. 363. That makes more sense. This is the last possible multiple of 11. That's also divisible by 3. So we can take out, so from 363, we can take out 1 11th. So we are left with 10 11ths. And at this point, we get 330 possible values. And then every number after 363 is obviously not going to be a multiple of 11. So we get, sorry. Okay, we get like 337 total. Now we can also take out multiples of 101. Note that it's not going to be both the multiple of 3 and 11 and 101 because that's way larger than 111. That's going to be like 3, 3, 3, 3. So we can just take out the 3 values that are both divisible by 3 and 101. This will be 3 times 101, 3 times 202, and 3 times 303. And then anything bigger than that will be bigger than 1111, so we don't need to worry about it. So we do 337 minus 3 and get 334. That's what we get for the second case. So the first case we got 6,000. The second case we got 334. Third case we got 555. And the last case we got 0. Why? Because our max possible value is 101. But for something to be divisible by 101 and not 9 or 11, it needs to be bigger than 101. And this is just impossible. Okay. So after looking at these 4 cases, note that we can't have any more possible numerators because we've already taken into account things that are divisible by each of these. And if you take, for example, things that are divisible by 33, you're going to end up in a similar case to case 4, where the multiples of the denominator are bigger than the max possible value of the numerator that you have set for yourself. So our total number of values that we can possibly have is just a sum of what we got for each case. So this is 6,000 plus 334 plus 55. Wait, no, we missed 3. Oh, okay, so we can probably do 33.
Multiples of 7 and 3, right? So 33.
Okay, so that would make a denominator of 101. Yeah. So, okay, when we have a denominator of 101, we get, we want things that are divisible by both 3 and 11 and not by 101. So then we get 33, 66, and 99. So this case gives us 3. Okay, set. And now, after getting all of the cases, we get 6,392. And that's our answer.
Is the answer a 4-digit answer, Shreya?
It's not. They asked for n mod 1,000. Foreseeing this, obviously, and
Okay.
I didn't foresee it, so we take out this.
392?
Yeah.
Yeah. Oof. That was a long problem. Long solution, yeah. You did it.
Yeah.
Yay. Yep. Thanks everyone for hanging around with us on Sunday evening for about 3 hours. Yep. Someone else is, yes. Is it you? Yeah. So I think we are done. Does anyone have any last minute burning questions? Any comments, feedback? AIME is the highest level in the high school competition, so no wonder it took us this long, 4.5 hours to just solve 15 questions. So thank you, Shreya. I really appreciate your efforts. Anyone if you're willing to be on the team with us to coach other kids, if you think you're AIME material or you know someone who has taken AIME several times, please email us at coaching@northsouth.org. We would love to have you on board. We are looking for volunteers to run the summer AIME Prep Club, if we can have one. We're not sure. It will be great if we can. But we need more people to volunteer for that who know what they're doing, like Eric, Shreya, and Sirash. So we'll see. All right, stay tuned. We may have an AIME 2 session too. There are 2 AIMEs per year, AIME 1 and AIME 2. So we did AIME 1. We may have an AIME 2 session too. I'm not sure. We are still working on if and when we can have it. I think that's basically it. So Vinay and Daisy uncle, anything else?
Does anybody have any comments or suggestions? Or so I think we have 1 more minute, right? So there was a poll question about like the participation in AIME and other stuff, right? So if as feedback, Daisy, usually you request feedback for the session, right? So if they can actually share with us those, then we can incorporate in either starting the summer workshop or Sri Priya, also going forward. You were also looking to see if we can have a workshop for the AMC levels as well, right? So it was too late last year, right? But then if you were considering anything like that for this year, then I know a lot of participants probably have good experience, like having taken AMCs already. So if they want to, if they're willing to volunteer for that.
Yeah. So if you want to do coaching sessions like this, like you might have seen that we have had live solving sessions for AMC 8, AMC 10. I don't think we have had one for AMC 12 yet in the last 2 years, but we want to promote all these, higher level competitions among our membership. So if you have taken these tests multiple times, or you know anyone that has taken these tests multiple times and would like to have the joy of doing one of these sessions, just email us, coaching@northsouth.org, and they will get it to me and my team who are organizing these sessions, and we will be happy to have more people join us. Absolutely. And parent volunteers, if you are, I'm a physician, so I'm not a math major at all by any means, but I started doing this because my kids have been doing competitive math. And we have struggled to find the right resources and right group. That's what motivated me to form our team, and we have a wonderful team. More than a dozen members who are actively working year-round on multiple things, including these kind of life-solving sessions. So Vinay is our honorary member now because he has helped us put together so many of these sessions in the last few months. So parent volunteers, if you're strong in math and want to help our kids grow and develop passion for math, please reach out to us. On resources for preparing for these tests, there are many resources. One good place to start is just looking at the past AIME problems. Google and go to Art of Problem Solving website. They have all the past AMCs, A8, AMC 10, AMC 12, AIME, all the past questions with solutions. Sometimes even more than one solution for a problem. So that's a good starting place, but there are also several books. There will be local chapters, like in where you live, just reach out and ask. There could be NorthSouth chapters, so where you can meet other similar-minded kids and families who do competitive math. Please do our NorthSouth competitions. That's a starting point, and we will just nurture you through your journey. And you could also find local math teams. Like one of the teams that we found here where we live is the ARML team, American Regional Mathematics League. So you just have to keep your eyes and ears out and look for these kind of resources. Anything else you want to add, Vinay?
Yeah, that's all. I think I just wanted to see if they, having the experience that they have, if they are willing to volunteer for the AMC sessions, that would be helpful. Thanks.
Yeah. Thank you for being with us, and have a good evening. The new week starts tomorrow. Bye-bye.